back, 12U Bio. Hope you guys had a good weekend. So what we're going to go through now is just some of the, again, basics of chemistry as we go through. And again, it's biologically based chemistry. So you're going to go through the content that I have below here. But I'm going to kind of give you kind of an introduction to what I think, are the key points of this lesson. Okay, so we're going to be talking about organic chemistry here. Now, organic chemistry is really just the chemistry of carbon. It's the chemistry of living things or things that used to be living. Okay, if you've taken 12U chemistry, you're well educated in this. If you haven't, we're going to go through some of the basics. Okay? So organic chemistry is often called the chemistry of carbon, okay, because it's every organic molecule, and all the molecules we talk about, carbohydrates, lipids, proteins, nucleic acids, and those are going to be the focus of this unit, are organic molecules. Okay, and when they're saying they're organic molecules, it means that they have to have a carbon backbone here. Okay, so all organic molecules are going to contain what we call a carbon backbone. So here's our carbon molecule, and just reminding ourselves it can make 4 bonds. So here's one of our macromolecules. This is glucose. And if we look at glucose, and we're going to look at all the different macromolecules, you're going to see that there's a carbon backbone here. So you can see there's carbon attached to a carbon, attached to a carbon, attached to a carbon, attached to a carbon, attached to another carbon. We call this the carbon backbone. And a lot of the molecules are going to be like this, where it's just a series of carbons attached together. And that's the basics of an organic molecule. Okay, now, all 4 macromolecules, okay, so here's again, this is an example of a carbohydrate, but all 4 macromolecules are going to contain a carbon-hydrogen backbone, okay, which is a series of carbons connected. Now, there's some little formatting things that I really want you to pay attention to. So this is showing every single carbon and hydrogen drawn out by representing C's and H's. Now, because we have so many carbons and hydrogens and all these different molecules, we've created a short form for them. So here's the exact same molecule, but drawn a little bit shorter, where every single time there's a change in direction of the line. So see this point right here, how it was straight and then it goes on an angle. At that point, we as chemists represent that there's a carbon there and the appropriate number of hydrogens attached. So on this picture, it actually shows that there's a carbon there, and there'd be 1 hydrogen attached here, another carbon, and then an oxygen, and then a carbon. Here, it just shows basically nothing, and that represents there's a carbon there, there's a carbon here, 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 here. There's obviously not a carbon there. Okay, it's just a shorter form so that we don't have to draw out these carbons every time. Right? So I'm going to show you a couple more examples. So here is an example called butane, and it would be a bunch of carbons all attached together. This is another way of writing butane. Okay, this is the most conventional way of writing it. Okay, it doesn't look like much; it's just a bunch of sticks. But this is a faster way of representing that there's a carbon here, 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 and here, and the appropriate number of hydrogens. Okay, because the carbons on the end are going to have 3 hydrogens to make the 4 bonds, where the interior carbons are only going to have 2 hydrogens because they're going to be attached to 2 other carbons. Okay? Now we can also represent these in ring structures. So here's an example of a carbon-hydrogen backbone. Okay? But instead of drawing out all of these carbons and hydrogens, we can simply represent it as this. Okay? And this represents the exact same thing. Okay? Chemists would recognize that at every point there's a carbon and a number of hydrogens associated with it. Okay. So when we draw and we see these macromolecules like carbohydrates, we're not going to see all the carbons listed in there, but we have to recognize that there are carbons there. So here is an example of sucrose or table sugar. Okay. And although there's not carbons written in here, every single time there's a point, there's going to be a carbon there. Okay. This is a lipid or a fat. And see all these little lines right here? These are all carbons and hydrogens, carbons and hydrogens, carbons and hydrogens. Okay. And there's some double bonds in there. Anything that's not a carbon or hydrogen has to be labeled. So if you have an oxygen, you label that there's an oxygen, because if you don't label anything, people think it's a carbon and hydrogen. So anything other than carbon and hydrogens will be labeled. And you can see that on the sugar molecule. Here's an example of our nucleic acids. Okay, so every little point here, there's going to be carbons. And if there's not a carbon, they'll label it. So there happens to be a nitrogen, and then a carbon, then a nitrogen, then a carbon, and then a nitrogen. Okay? Here's some protein. Same kind of thing, carbon, carbon, carbon. And then anything other than carbon is labeled. This doesn't show the stick one. Okay? So all our macromolecules are going to have a carbon backbone placed to them. Right? Now, the importance of functional groups. So a carbon-hydrogen backbone is very simple and incapable of performing any function. So what we have here, just carbon and hydrogen. There's not many things it can do. It's relatively unreactive. It's nonpolar, which means it won't dissolve in water. And it's really stable. It won't react very much. Okay? Well, in order to provide function to the carbon backbone or functional group, we add these things called functional groups. Now, there's a lot of different types of functional groups. Okay? One that I have here is an OH group. Okay? So this OH group has been added to our normal carbon backbone, and this is going to provide function to it. It's going to change this molecule into something different. This one's going to be a lot more functional and provide a lot more functions to the body than this one does. Okay? And when we add these different types of molecules to the carbon-hydrogen backbone, we call them functional groups. Okay? So functional groups are groupings of atoms that provide function or change to the carbon-hydrogen backbone. Okay? This is where the other elements are going to be involved. When we have nitrogen or oxygen or phosphorus or sulfur, every time these get added into a normal carbon-hydrogen backbone, then it provides function. So when we look at a sugar molecule, okay, I have some functional groups here. I have an oxygen, okay, that's been added. I have an OH group that's been added here and here and here and here and here. So this sugar molecule is a lot more functional than just a straight carbon and hydrogen ring. And those are the importance of functional groups. Okay, so when we look at functional groups on all of our different molecules, I already located some here on carbs. Okay, here's a functional group on a protein. Again, anything other than a carbon-hydrogen bond. So right down here, there's no functional groups between this carbon, this carbon, and this carbon. But here's a functional group. Here's a functional group. Here's a functional group. There's a functional group. Here's a functional group. Here's a functional group. If we look over at lipids, all of this stuff right here, there's no functional groups in there. But as soon as we see this oxygen, here's another oxygen, these double bonds, right? These are functional groups. They're going to provide function to this molecule. Right? All right, and that's our video on short, kind of basic organic chemistry. Now, our next one is going to be on the chemical reactions. So make sure that you look at